Welcome. Today I'll be presenting our paper titled Meta-Reasoning and Path Planning for Autonomous Indoor Navigation. This was work done with Professor Susan L. Epstein at the City University of New York. I'd like to start with a motivating example. Here we have a robot located at the star and its target is at A. In the real world, this can be a very far distance. In this example, that's 65 meters. And for industrial robots like those in our lab, their sensor range is only 25 meters, so the target is not within sensing range. In fact, the robot's knowledge of the world is purely this white box. It doesn't have any other knowledge other than the distance that it is to the target without a map. This world is actually much more complex. This is the 5th floor of a building in Manhattan, the size of a city block. And this world has many narrow doorways. There's jogs in the middle of hallways and other support columns that the robot has to contend with. We believe that this task requires careful maneuvering, learning from noisy or incomplete perception data, and balancing multiple objectives. And so this task requires path planning. And there are many possible paths that you could take given such a map. You could follow this route. Here's a second example, and here's a third example. Our system, Semaphore, instead learns a spatial model in this same world and then can use that model to plan hierarchically to get from where it starts to its target. This model can be learned during task execution or at the end preliminary from exploration. So Semaphore is a robot controller for autonomous navigation. And the thesis of our work is that a robot can efficiently learn, robustly plan, and effectively navigate in challenging worlds. And as I mentioned in the previous slide, the robot's task is to travel to a target, given its pose, which is its location and heading, and a spatial model, but no map. Semaphore learns its spatial model from its local perception data online in real time, and then can use that model to hierarchically plan in free space. And then also can opportunistically intervene with meta-reasoning. In this work, we call, for robot navigation, we call a world indoor built two-dimensional spaces. And the robot's perception is a laser rangefinder with a 25-meter range. A decision point is the robot's pose plus its laser rangefinder data, as seen here. And a path is an ordered sequence of decision points. And here we have an example of a path, which is the dotted line. And our system can also learn a trail, which is a refined version of that path. Traditionally in robot navigation, a plan is represented as a sequence of waypoints to the target, which are individual specific locations in space. Our spatial model is focused on where the robot can move, not what impedes it. And it's learned in real time from the robot's experiences. And we generalize over that experience to create a model that's not precisely mapping the architecture of the world, but instead is learning spatial affordances, which we expect to facilitate navigation. And here are some examples. We have regions, which are represented as circles of unobstructed space. We have exits, which are points on the circumference of the circle where the robot crossed, and doors, which generalize over exits to represent ways in and out of that region. You can also learn a skeleton, which is a graph constructed on the regions, where the regions are the nodes, and we have an edge between the two regions if the robot ever traveled between those two. So the novelty of our work is that we're able to plan hierarchically in our free space model, which is the skeleton, once for a target. And that plan is actually robust to sensor and actuator error because it's generalized over the robot's experiences. Using that plan, we can then operationalize when we need to execute an action. And we've replaced waypoints, which are single points of space, with continuous space, our regions. This allows us to facilitate novel shortcuts, and if the robot is confined, extricate it. This work also addresses complex large worlds with only the robot's laser rangefinder and no map. So here's an example of the free space plan in the skeleton. We have the robot at the bottom of this world represented as the red square. It's not in a region. We also have the target at the top here represented as a star, also not in a region. Our planner then constructs a sequence of regions as the plan for the robot that it's able to follow to get to its target. However, when it comes to operationalization, moving from one region to the next may not be a straight line. Instead, we save the trails between two regions, which is the refined version of the path to get from one region to the next. And then we can, when we operationalize, if needed, we can pull out the trail and use that instead to travel between. And I'll show you another example of that here. So this is an example of a plan for the robot which goes from region A to B to C. There's no edge that exists from A to C because the robot never traveled that way. However, when the robot gets to region A, it's able to sense region C, take a step, and go there directly. And we call this a novel shortcut. And many psychologists believe that this is a sign of intelligence. Here's another example where we have two regions, S and T. The edge between them appears to go through a wall, but when the robot arrives at S and operationalizes, it can then pull out the trail between those two regions and use that instead. And the trail can then be decomposed into individual waypoints. Out is our reactive planner, which responds when the robot is confined. So here's an example where the robot's original plan to its target starts at W and follows the sequence of waypoints along the yellow line. The robot has been confined in this room for many decision points at A, at which point out will trigger and create an escape plan from 1 to 2 to 3. When the robot starts to follow this plan, it takes a few steps towards 2, at which point it can detect waypoint D. It then takes a step towards D and is able to, again, take a novel shortcut by skipping both waypoint 3 from out and its original waypoint W. Here's an example of our robot following its plan in real time. The robot is surrounded by a red circle, the regions are the green circles, and the pink dot is its target. And the robot just achieved its target, and this time that we're waiting now is the time it takes for the robot to update its model and plan to its next target. Nearly instant. We conducted an experiment in simulation with Ross in 3 worlds. Here's the first one, M5, which is the 5th floor of the Museum of Modern Art in New York City. The second is H10, which is a large office building in New York City. And of course, G5, our original example. All 3 of these are very large spaces, at least the size of a soccer field. For each of the 3 worlds, we generated a sequence of 40 targets randomly, and we generated 5 of them for each world. And we implemented a decision step limit, 500 for M5 and 750 for the other 2 worlds. And we determine if the robot is successful at a target if it achieves that target within the step limit. Our evaluation metrics were time, distance, and success rate. Here's the results for success rate. We conducted an ablation experiments. We looked at different versions of our system. The first bar that you see here is the purely reactive approach, which uses a simple procedure, which is if the robot can sense its target, take a step towards it, otherwise select a random action that does not collide with an obstacle or oscillate the robot in place. As you can see, this is not very successful in any of the 3 worlds. The second bar is our plan-free approach, which learns and uses the spatial model, but without planning. And it's much more successful in M5, getting over 90%, but not as successful in the other 2 worlds, which are larger and more complex. Semaphore is our full system, which includes planning, and you can see it improves significantly the success rate in all 3 worlds. As I mentioned at the very beginning, we can give Semaphore some preliminary exploration time in which it's able to build an initial version of its model to plan in. And these are the 2 bars that represent 20 and 30 minutes of exploration, which significantly improves success for H10 and G5. Our system is able to make decisions in real time, construct its model quickly, and efficiently plan in it. Here are the results for distance and time. Distance and time are significantly reduced in M5 when we introduce planning. However, for H10 and G5, distance increases because the robot has to travel further to follow its plans and get to the target. However, time is actually reduced for H10 when we introduce planning. And when we do some preliminary exploration, time is also reduced in G5. Currently, we're working on additional reactive planners that address other situations and some novel spatial affordances that will also facilitate planning in free space. Our take-home message is that an operationalized hierarchical free space plan can contend with error, take novel shortcuts, and plan reactively to support robust navigation in complex real worlds. Thank you.